Please welcome our 2025 SIGGRAPH Conference Chair, Ginger Alford.
Thank you. Good afternoon, everyone. It is my pleasure to welcome you to this special address from NVIDIA Research, where together we'll explore the next frontiers of graphics and simulation. Joining us today on the SIGGRAPH 2025 stage are Sanja Fidler, Lefohn, and Ming-Yu Liu. Together, they are at the forefront of breakthroughs in neural rendering, world foundation models, and generative AI, technologies that are reshaping industries from media, manufacturing, to robotics and automotive. But first, please enjoy a special message from NVIDIA.
Coming on. Oh, I can feel it.
Hello, SIGGRAPH. It's great to be with you. We're living through extraordinary times. AI is reshaping every industry. AI is essential infrastructure, like electricity and the internet. This revolution is powered by the GPU, the heart of a new type of computing, one that could solve problems normal computers can't. And it started with graphics. SIGGRAPH has been with us every step of our journey. In 2001, NVIDIA invented the world's first programmable shading GPU. On November 8th, 2006, 5 years later, we introduced CUDA, turning the GPU into a programmable accelerator for complex algorithms. CUDA GPUs made first contact with modern AI, the AlexNet, in 2012. Then in 2018, right here at SIGGRAPH Vancouver, I introduced RTX and brought real-time ray tracing and neural rendering to the world. Built on the work of the late Stephen Parker, RTX fused programmable shading, ray tracing, and something completely new: DLSS, generative AI for graphics rendering. Graphics processing GPUs enabled AI, and now AI is revolutionizing graphics processing. A new way of doing computer graphics was born: AI inferred pixels versus 3D algorithm calculated pixels. With the first DLSS, 1 out of every 4 pixels were calculated. 75% of the pixels were inferred. Today, DLSS AI infers entire frames, inferring 15 out of 16 pixels. RTX has transformed gaming, visual effects, virtual production, product design, and beyond. And now, physical AI and robotics. Robots don't learn from code, they learn from experience. But real-world training is slow and expensive. So we teach them in virtual gyms, simulations of the real world, with synthetic data generated by AI models. Today, NVIDIA research leaders, Lefohn, Sanja Fidler, and Ming-Yu Liu will highlight NVIDIA's research on AI for graphics and graphics for AI. I am so proud of the NVIDIA researchers showcasing their work. There's a reset in computer graphics. The field is wide open for fundamental breakthroughs again. And because digital twins and virtual worlds are so foundational to physical AI and the future of robotics, I expect to see an explosion of new ideas at SIGGRAPH in the coming years. The SIGGRAPH community has been part of our journey for the past 30 years. It's a privilege to be with you all. And now, let me introduce our first speaker, Aaron Lefohn, VP of Research in our Real-Time Graphics Lab. Have a great show.
Real-time path tracing, the simulation of the physics of light to create images. This was the holy grail, the point on the horizon for real-time rendering for decades. And 2 years ago, CD Projekt Red, game studio, in partnership with NVIDIA, launched world's first AAA game, path traced. Since then, many games, real-time applications, content creation tools have shipped with real-time path tracing. Real-time path tracing is here. And NVIDIA has increased the performance of real-time path tracing over 10,000x in the last 9 years. 100x of that is from improvements in GPUs and our graphics drivers. As Jensen said, we launched the first ray tracing hardware here in Vancouver at SIGGRAPH in 2018, and since then, there have been 4 generations of ray tracing cores, 4 generations of tensor cores, and entire new graphics API capabilities, like sorting while we're ray tracing. 10x of this is DLSS, deep learning supersampling, continue to provide speed-ups with super resolution and improving, now generating frames in between what the simulation is generating. 30x of this from rendering algorithms, especially important sampling, figuring out which rays to shoot, where to shoot them, and how to share the precious data that each one of those rays brings back. A ray shot today is worth over 30x what a ray was 9 years ago. Rendering algorithm research matters a lot. All of these pieces working together to continue to advance real-time path tracing. I'd now like to share with you real-time path tracing today. Let's take a look. What you just saw was the simulation of light physics on billions of triangles, unlimited numbers of lights, combined with real-time AI, DLSS. Real-time graphics today include sub-pixel microtriangles that we can accomplish because we can rebuild our acceleration structures for ray tracing, our bounding volume hierarchies, every single frame from scratch. That opens up the possibility now of doing something that previously was only available in offline rendering, displaced subdivision surfaces, and of course they're dynamic. If you want to see that, come see our entry in Real-Time Live tomorrow night. Real-time graphics today includes hardware-accelerated fur and hair primitives, and real-time graphics today includes a state-of-the-art in rendering algorithms. All of this is available in our SDKs for you to integrate into your applications, your research. And of course, DLSS. Let's go back to the slides. Jensen introduced DLSS here at SIGGRAPH in 2018, and it was world's first AI real-time graphics product. And now in that demo you saw, 15 out of every 16 pixels being generated by AI. Let's take a look. What you're seeing on the left and right should look the same. Don't look for differences. Look at the upper right in that number. That's without DLSS on the left and with DLSS on the right. Now that 1/16 of pixels that DLSS is not responsible for is very important. That's the output of the simulation. That is the rays that go out into the scene. You've simulated your world. You're now simulating light traveling through it. And you come back with this very sparse signal that we hand to an AI system to make the images. DLSS is now shipped in over 750 real-time applications and has transformed the image enhancement part of the graphics pipeline. So where do you go from here? What comes next? Well, I need a bowl of strawberries for that. The detail that our eye can see is extraordinary. And what creates the appearance of what we see in our everyday world are these incredible details that you get when you look up close at something. It's all of that together is what makes something look real. And so when you look at these strawberries, you see these tiny little hairs, every single one of those hairs. We don't usually model those in real-time graphics, but now we can. And you look at the strawberries themselves, and it's not just one reflectance function. You can see there's this waxy clear coat, and then under that, this reddish thing, and there's multiple layers, each one having its own properties of how it reflects light. It's true in the stems and those leaves, as well as the strawberries. But I am sure that the artists of you out there are looking at this and saying, Aaron, I could create that, and if I take one of the latest real-time path tracers, I'm sure that I could make that scene in real time, and I believe you. I know you can. But I need more than a bowl of strawberries. Strawberries are just one of the delicious things on this breakfast table, every one of them having that much detail. And it's not just what's on the table, it's the entire setting. Even that fiberglass chair, what makes that look like fiberglass, if you look up close, are the fibers of that fiberglass embedded in the resin. And never mind the dirt that's in that planter box. But this is just one breakfast patio and one apartment. There's a whole apartment building full, and there's a whole city full of those apartments, and that city lives in this forest. If we want to have computer graphics scenes that have strawberry levels of detail at city scale, we need to invent completely new tools so that artists can conceptualize, create, and iterate orders of magnitude more quickly than they can today. Generating 3D representations, we don't know what they are yet, that are orders of magnitude more compact in memory and compute than what we have today, and whole new ways of rendering that content, including generating some of this detail on the fly on the renderer. I'm going to share with you a step that we're taking to make this possible. 41 years ago, in 1984 SIGGRAPH, Rob Cook introduced programmable shading to the graphics community with the Shade Trees paper. 24 years ago, NVIDIA introduced programmable shading to real-time graphics. And this year, in January, NVIDIA introduced the next era of programmable shading, neural shaders. Neural shaders bring AI into the heart of the graphics pipeline, allowing you to execute neural networks in your shaders, allowing you to use the tensor cores in addition to our compute cores in graphics, and brings the pace of AI hardware and algorithm innovation to the rendering pipeline, attaching the rendering pipeline to the AI rocket. We've been publishing papers here at SIGGRAPH for years, as have many of you, on what we could do, what kinds of algorithms would be possible if we could run neural networks inside of a renderer, but previously you couldn't. Well, we've listened, it's here, and now you can. Neural textures providing 7, 8, 10 more X compression that's possible using block compression that's state-of-the-art today. Neural materials, neural radiance caching, and of course NeRFs, neural radiance fields. If you wanted to evaluate, put a NeRF in your renderer, now you can. To explain the power of this and what this means, really what this lets you do is invent completely new representations. The representations I was speaking of that we need to invent, this is a platform now we can do that. And let me explain with neural materials. I mentioned the strawberry having multiple layers. Well, almost everything we see in our world has complex reflectivity. The way it looks is a result of light reflecting off multiple layers within that material. I'll explain this with a gemstone. This is known as a star sapphire. And if we build this up layer by layer, we start with a base gemstone material, add the luster layer. This begins to give it its blue hue. And then we get this diagonal line. This is a result of minerals oriented in a specific way included in the gemstone that, for those of you rendering people, this is a highly anisotropic BRDF. And there are 3 of them, each of them on a different axis. And of course, there's a fingerprint on this thing because, well, someone put their fingerprint on this beautiful gemstone. But every one of those layers has a different set of textures and a different set of reflectance functions. And by the time you're done building this thing, it's over 20 times the cost of what is you typically see in a real-time graphics application material today. Well, we built this gemstone and other materials in Epic's substrate multi-layer material system, which is new to Unreal Engine. And then in a prototype of Unreal Engine we have internally, we added neural materials training, we added neural materials rendering so that we could bring this to life. Let's take a look. What you just saw when it said neural materials is that everything had been converted to neural materials. And what you saw when it said standard materials was the same artist who created those reference materials doing his best effort to create a material that looked the same but constrained to using the 1-layer model we have in real-time graphics before neural materials. Now, we showed this demo when we launched our Blackwell GeForce GPUs earlier this year, but we didn't say very much about it. But this is SIGGRAPH, so I get to tell you more. The performance of the neural materials, which is representing those references that were over 20x the cost of materials today that are 1-layer, matches the performance of what you see in a 1-layer material today in games. And I also get to explain how we train it, which we didn't say before. We said a little bit in a paper a year ago that we presented here at SIGGRAPH. The way these are trained is that we take your reference material, as complex as it is, doesn't matter, and we evaluate what happens when a ray shoots it. Reflectance samples. Same way you would gather data if you were measuring a real material in real life. We take all that data and we fit it with a neural network that can learn the immersive reflectance properties of the gorgeous creation that you made. All the data and textures gets converted to highly compressed neural textures. The reflectance function gets learned, represented in a neural network. Now, in this paper we presented last year, we reported it took 3 to 5 hours to train one material. Well, our programming model researchers and our AI algorithm researchers and our engineers have been busy. This now trains in a couple minutes, over 100x faster than we reported in our paper a year ago. One of the keys that makes that possible is this new programming system invented by both our language researchers and engineers partnering together, evolving the language Slang. Slang is a new graphics language. It's now a Chronos standard. It began as a collaboration between NVIDIA and Carnegie Mellon over 10 years ago. And I'm bringing it up now because Slang has something in it that makes it designed specifically for neural shading and neural graphics. all of the shaders you write in Slang can become differentiable. That means you can take any piece of your graphics code and put it into a learning system. Slang integrates with Python, it integrates with PyTorch, and it's optimized for neural shading, and is a big part of how we achieved this speed up. Neural shading brings AI to the beating heart of the rendering pipeline, extending AI's reach beyond DLSS into the renderer, and is ready for your explorations today. We cannot wait to see what you invent with this. To learn more about this, there's a whole half-day course on Thursday. Please attend. There will be lots of sample data put online, as well as the slides, and there's an SDK ready for download. Neural shading is here, and in particular, enables your creation of entirely new types of assets using the power of AI. So that's our strawberry, but we need scale. And if you want to create, for example, a digital twin of a factory to train next generation of robots, you'll have the geometry from the CAD, but you don't have the materials. And it needs to look like the real world to train those robots. So I'd like to share with you work that our researchers are doing to create AI assistants for material artists. Let's take a look.
Digital twins are vital for the training and testing of physical AI that can understand and perform complex actions in the real world. But today, building digital twins is slow and tedious, often starting with 3D models missing the detailed materials needed for training safe, efficient physical AI systems. NVIDIA's latest generative AI research empowers developers to transform the workflows of the designers and engineers at the heart of these efforts. Soon, 3D experts will select models inside their preferred CAD and simulation software and engage AI assistants using simple language to describe their requirements. These AI assistants combine NVIDIA Cosmos World Foundation models and rendering technologies to quickly generate base materials, complete with realistic visual details including reflectivity and surface textures. From here, experts will fine-tune the base materials to accentuate realism, hand-editing properties like roughness and textures to add details that better reflect the real world. Through this seamless collaboration, 3D models are transformed into large-scale, physically accurate digital twins, ready to be used for simulating and testing advanced autonomous systems. These breakthroughs bring developers one step closer to AI-assisted workflows for accelerating the development of digital twins and safe and efficient physical AI.
AI assistants for artists, just like we have, for those of us that write code, AI assistants for helping us code. And since this is SIGGRAPH, I get to tell you how it works. When you use this AI assistant, you have, for material generation, you have the geometry and a prompt. And so we combine rendering, differentiable, learnable rendering, and the Cosmos World Foundation model together to make this work. We'll render that geometry, we'll create videos. Those videos don't contain colors, RGB colors, they contain normals and position. We hand those videos to Cosmos and the prompt. It taps into its rich knowledge of what the world looks like, and we've modified this version of Cosmos to be able to generate materials that look like the request of the prompt. It outputs video buffers, videos that contain the material properties. And for those in real-time graphics, these are G-buffers. For those of you not real-time graphics, G-buffer means geometry buffer. These are images that make up videos where the pixels contain the material properties of the geometry that hit that pixel. Once we have these videos, we can project using a differentiable renderer back into 3D and have a 3D material. Now we can apply that to geometry, import that into our favorite content creation tool, and the artist can work from there. To create this AI assistant, we start with a data set of 3D models and materials and generate those same video G-buffers I told you about, but also the references that it needs as the images and the material buffers. And we fine-tune Cosmos to output and teach it to output the material parameters that it synthesizes. And we also, with a differentiable renderer, create an image of that so that Cosmos learns from both of these, and it can learn the correlation between the material parameters it outputs in 2D and the final rendered result. All of that can be backpropagated through the renderer, because it's a differentiable renderer that we wrote in Slang. Rendering, differentiable rendering, and Cosmos working together are able to tap into Cosmos's deep knowledge of the world that it typically outputs in 2D and bring that to a 3D asset. AI is transforming graphics, all stages of the graphics pipeline. And graphics is transforming AI. As I showed you in this last example, with graphics and AI together, graphics is teaching AI 3D. And the next era of AI is 3D. With that, I'd like to introduce my colleague and friend, Sanja Fidler. Sanja is VP of Research and leads the Spatial Intelligence Lab, and she'll be telling us a lot more about AI in the physical world. Ladies and gentlemen, Sanja Fidler.
Hey guys, thanks for having me. I know it's not Jensen, but here's the mandatory leather jacket. I know. All right, let's get started. So in the past few years, we saw the rise of a new era, the era of generative AI. GANs, diffusion models, empowered creativity. I mean, Aaron just showed you a couple of really cool results. And the invention of transformers led to ChatGPT, which really was the inflection point for generative AI. Now, today, many of these so-called foundation models are in wide use. Literally hundreds of users are interacting with them every single day. Large language models, vision language models, multimodal models. And these are really considered as building blocks towards something even bigger, the agentic AI. We try to empower users to solve complex problems or accomplish complex tasks with this like web or chain or web of agents just working for the user. For example, I want to go to Australia next week. Go, 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 AI minions, find me the best itinerary. Now, is there something that follows? So what is next? The next is the era of physical AI, the era of robots, bringing digital intelligence into the physical world. Well, all these models need to work together to make that happen. Sensing, reasoning, planning, and action. Robots that are going to assist us in our homes, redefine how work is done in factories, warehouses, agriculture, and more. The next gigantic market. All right, so actually, this very community envisioned robots through animated movies for several decades. In fact, when I was a little kid, I grew up with these movies. And wow, you know, like at 6 a.m., this robot that never complains can take a dog for a walk, and you can just sleep, right? Or take like stinky trash out instead of you. So it was really exciting. I went even as far as convincing my sister to dress as a robot for Halloween. Yeah, and she took all the earnings. So who would have thought that I would be actually here today talking to you about robots? And my sister is an economist. All right, so simulation here in the middle really plays an important role, right? So physical AI can scale through real-world trial and error. It's unsafe, time-consuming and expensive. Robots break. During development, robots break things, right? Whereas in simulation, they can be trained in this parallel virtual environment without any harm, right? Things don't break in simulation. The robot can crash in 1,000,001 times, and nothing happens. It's basically just game over. And importantly, also simulation time runs orders of magnitude faster than real time. So what would have taken a robot to train maybe 10 years in real life would now take them only a few minutes. All right, so let's switch a little bit to the world of robots. So the utility of robots really depends on the complexity of the environment they can operate in. So what does that mean? I could have a completely blind robot over here, just basically nothing here, just a simple plane, doing something as complex as a somersault, which probably many of us cannot do. At least I cannot do. I tried once, and I went to computer science instead. But it's not a very useful robot, right? So what makes a useful robot? For example, say driving cars. Wake up in the morning, call my car, it comes from the garage, brings the whole family around to all the destinations. It's essentially never tired, never complains, never distracted, operates 24/7, right? However, to build something like a self-driving car, it needs to be able to operate in very complex environments, right? A road, so much traffic going on, there's an aggressive driver on the left, on the right, cutting in, harsh braking. Humans, maybe kids, can step on the road at any time. Animals, it's very, very complex environments, even though we drive there every day and maybe we don't even perceive it as so. And kind of the following up, the more and more complex environment, the more and more Earth and tasks we want to sample, the harder it gets, right? There's the holy grail being a generalist robot. It can do a lot of different tasks. And typically, we envision it to take the form of a humanoid. So these skills are really hard, in these complex environments, are really hard to learn for robots. Now, what is even harder, or equally hard, or even harder, is actually simulating these environments. And it's actually in your power over here to help make that a reality. Just a very high-level overview of the robot so that we can all be on the same page. So language model essentially produces text tokens, right? You give it a prompt, maybe a question, or maybe even an image, and produces some words. For robots, they're producing action tokens based on some sensory input, for example, recording around me, and some intent, bring me home, taking highway. Action tokens, for example, steering command, right? Or something like waypoints where the car should drive in the next few seconds, given how I sense the environment, and that would be a safe move. So as a proxy to the real world, now the simulator takes the current state, the new action that comes out of this model, it's called the policy model, and then produces simulates the next world state, and then renders it out into sensors, and then off you go, it basically repeats. It's kind of like a game engine, though it's actually fundamentally different than a game engine. There's basically no forgiveness for a robotic simulator. Everything needs to look like the real world. So the virtual world needs to react to the robot in the exact same way as the real world would. Otherwise, we're teaching it something wrong, and it would not be safe to deploy that robot. Or it would take us a lot more time to actually verify it by deploying it in the real world. So today we're going to talk about simulation, how we're thinking about it, and how hopefully you can help us in the future. So we're going to take Aaron's diagram, and we're pretty much going to follow it in that high-level description, but we're going to also change it a little bit. So the content creation part, we're going to do that a little differently, because at the end of the day, we need to bring the real world into simulation. And that is actually going to change all the AIs in little boxes that follow. So we discussed that we need to simulate the real world as faithfully as possible. So one way to minimize the reality gap is actually to bring the real world into digital form. Go out, put my robot car in the real world, drive it, actually record events, real world events, bring it home, and actually make that into a simulation environment such that this training robot on the cloud can actually try again until it gets it right. Let's talk a little bit about the requirements and what it would take to make this work. So the real world is actually really large, right? So you can actually travel a couple of kilometers in just a few minutes, especially on a highway or something like a racetrack over here. So our algorithms need to scale with the size of the physical world. The real world is also highly dynamic and very diverse, right? So many things can happen in basically just a split second. So from highway to intersection, school zone, night, day, different weather conditions, our algorithms really need to scale to this complexity of the physical world. Bottom line, graphics need to scale and needs to bring the real world into simulation. All right, so Omniverse NeuRec turns real-world sensor data into fully interactive simulation, which the robots can then train in or test on. And it includes different tools and AI models for reconstruction, simulation, rendering, and enhancement, similarly to how Aaron talked about it. And really, it builds on some of the foundational technology that came out of SIGGRAPH. We're going to use Gaussian splats and some physics solvers that all now need to adapt to maybe this workflow. So getting real-world capture into digital form necessitates two key components. One is visual understanding that's going to operate on the sensor data, and then world reconstruction that lives that into 3D. Essentially reconstructing the scene into millions or even billions of particles that can then be moved around and manipulated during simulation. All right, let's kind of dive in. So let's first talk about understanding. The visual understanding of the world essentially operates at the space of the sensors. So this could be cameras, right? Videos coming out of cameras or LiDAR scans. And we kind of infer a couple of different things. One on the left is 3D cuboids. So you want to detect every single object that you want to later manipulate. And you want to track it over time, because that's going to give us object permanence during simulation. We also want to label, essentially, very, very detailed pixel every object. So when we put it in 3D, it's nicely delineated and well reconstructed. And of course, we kind of want to mimic the graphics pipeline Aaron talked about. So we want to also estimate all the attributes, or many of the attributes the graphics pipeline use. For example, physically based materials, albedo, metallic, roughness, and so on. One thing that is very important to stress here is that visual understanding is not perfect. And because of different ambiguities, it's hard to perfect. Probably it's even impossible to perfect. However, that should be OK. So all the algorithms that follow essentially need to be robust to that imperfection. The world reconstruction component essentially lifts all this 2D information into 3D. I have to stress that this is not as easy as it sounds. It's not like you go around with a phone and you can construct and get beautiful Gaussians out. Why is it hard? Because I have this data is typically corrected with a moving vehicle. This vehicle can drive 50 kilometers per hour, maybe 100 on a highway. So literally, it can drive meters between different frames. And other objects are also moving with their own velocities. It's hard. Cameras oftentimes have rolling shutter that can be outside the car, behind the windshield. That creates distortion. Camera poses as the car moves, very noisy, especially in tunnels. So whatever you get into 3D is going to be hard. These algorithms need to be robust. Maybe I'll play the video and then I'll tell you a little bit about how we do it. So one thing in the beginning, this is just to show you that it's not real. So we really need everything that a graphics pipeline uses, right? So we need the surface mesh for essentially physics, right? The car needs to move on the ground, go over speed bumps, and so on. You need to model the appearance, and we kind of divide it up between background scene, things that you don't necessarily need to simulate. And that doesn't mean that it's not dynamic. That could still mean the tree branches could be moving with the wind, or, for example, the traffic light could go from red to green or vice versa. And then we also reconstruct each individual object separately because we want to be able to simulate it later on. And we also lift all the graphics components into 3D such that we can manipulate the scene, for example, relight the scene. All right, the next component is to simulate the next state based on the robot's action. And this is really possible because of this editable Gaussian representation and some new physics algorithms that now need to operate in this particle Gaussian representation. So standard solvers actually don't quite work out of the box. So for a robot car, we're going to look at that on the left. We need to simulate novel trajectory, so the car decides to drive a little differently. We need to render that world in that camera pose. And at the same time, we need to manipulate all the dynamic objects with the right behavior based on what the car actually did. Let's maybe play. So here are 4 different drives where we are manipulating the other agents as well as the car decides to drive just a little differently because of that. Same scene, it was just original video, and now we want to simulate multiple times. For manipulation robots, it gets a little harder, actually, because the robot now wants to start touching things, right? And that needs to start feel and react the same as in the real world. I would say this still remains a very open question. Which brings us to rendering. So Gaussian splats operate with rasterization. And that's not quite enough for us here. Why is it not enough? So we use Omniverse RTX render to bring ray tracing into the game for more complex lighting effects. For example, shadows and reflections. And why is this important? It actually allows us to add synthetic simulated objects into the scene, such as this burning car here, synthetically added, or this object here with stuff falling out of this car. And that is actually really important to test the robustness of the robot. And it will be so hard to actually capture this stuff in the real world, right? Especially during development when you only have a couple of development cars driving around. So hard, but so important to test it because who knows? When we actually deploy these robots in the world, this might actually happen. So we need the robustness to this. All right, so I talked about PBR materials. Why? Right? We want to have all the same affordances for this 3D reconstruction Gaussian world as we have with kind of the standard graphics assets. Even though I maybe captured my scene in the early morning, I want to be able to simulate every time during the day, right? Again, testing a different type of robustness to lighting. So here, remember, we use computer vision to infer all these attributes and lift it to 3D, and those have imperfections. So what does that mean? We actually use generative AI. We use something called diffusion render. It's a diffusion model that's going to take this rendered PBR materials that we inferred and lifted to 3D in the novel viewpoint that the robot is actually requesting, these intrinsic properties, then a novel light that we want to simulate, and then we use a diffusion model to essentially generate the pixels of the same scene but different lighting condition. Now, obviously, you guys in graphics have this for a living. You see these things every day. But actually doing this for capture data, this is the hard part. Let me play a video here. Original lighting, and now we're going to change the lighting in the same environment. I think it's some scene next to the NVIDIA office in Santa Clara. So even though the PBR materials are essentially in a space which graphics algorithms in principle work, they actually don't produce really good results because of all the noise that's in that data. And that's where the generative AI comes in, and it's really important. All right, finally, the reconstruction approaches are really kind of like a hostage of the pixels that you recorded in that original video, right? So larger deviations, if the robot is requesting a large change, for example, it wants to move the lane one to the left, let alone 2 lanes to the left, then we need to render that in that viewpoint, and that is often hard for these approaches. It leads to artifacts. And we can't really afford artifacts. Again, we're going to be teaching robots something wrong. So here we're again going to use generative AI that's going to use this kind of corrupted render image and reference view so that we kind of ground it with reality and produce an improved result. Here is a couple of examples. So on the left, this is the original rendered view. You can kind of notice this zigzag on the crosswalk. And that gets better. And that really gives you like a 2-lane change, which is often enough for robot testing, at least. The same technique actually also works for inserting objects in the same scene. Imagine I harvested some objects in different videos with different lighting conditions. Now I can just naively place them in this scene, and this model is going to kind of do its job to make it look good. Add shadows and fix the colors. OK, so maybe it's time to actually put it all together. Let's take a look.
The world is entering the era of physical AI, transforming the way we move, and simulation is driving the field's latest advances. To test autonomous vehicles, real-world data is transformed into Gaussian-based 3D scenes, using Omniverse neural reconstruction, or NVIDIA, converting video into photorealistic digital environments. The reconstructed scenes are then simulated with variations to assess the AI driver's ability to generate safe trajectories. Physical AI isn't just driving on roads, it's operating in kitchens, offices, and warehouses. Each of these robots needs to be simulated in virtual worlds reconstructed from multiple sensors. With NVIDIA, we can rapidly render these simulations in real time with high fidelity. New capabilities like physics bring realistic interaction to 3D Gaussian scenes, letting robots engage naturally with virtual environments. Generative AI uses the visual properties in these simulations to add diversity, scaling a single scene into many. Neural reconstruction is already advancing the world's physical AI. And now, with just a text prompt, NVIDIA and Cosmos can generate 3D simulation environments that refine testing and validation for the next generation of robotics.
Thank you. All right, we're open sourcing. We're open sourcing a lot of the components that you have seen to empower all of you that are already building physical AI and all the researchers in the audience to make these tools even better, far, far better in the future. So with that, I'm going to welcome the next speaker, Ming-Yu Liu. He's a VP of Generative AI at NVIDIA, and he's really the cool guy that's building all the big vision models in the company.
everything that moves is going to be a robot. For different robots, we have different expectations. There are two axes of expectations. One is the environment diversity that we expect a robot can operate on. The other is the number of skills the robot possesses. For an industrial robotic arm, we only expect it to work well in a station, in an assembly line, performing simple tasks like picking and insertion precisely. For an autonomous vehicle, we expect it to work well in all sorts of traffic conditions, as well as steering, acceleration, braking, and lane changing. We have the highest expectation on humanoid robots. We want them to be like us, possess many skills, can operate in all sorts of environments. How do we build a humanoid AI to meet the expectation? If the success in generative AI can be transferred to physical AI, then the key will be on training data curation. ChatGPT and Gemini are so powerful because they have a tremendous amount of high-quality training data. How do we create a condition to have a tremendous amount of high-quality data to train physical AI? We have these chicken and egg problems. We don't have humanoid surrounding us to help capture data. Because we don't have captured the data, we can build a high-quality humanoid AI models. Because we don't have high-quality humanoid AI models, people are not buying humanoid robots, and we cannot collect data. We have chicken and egg problem. We believe the key to break this deadlock will be on synthetic data generation. We should leverage generative AI to create high-quality, large amounts of training data for physical AI. And my part of presentation will be on this, how we use Cosmos World Foundation model platform to help people curate high-quality training data to build physical AI. So this slide shows our physical AI data pyramid. We have a large-scale, internet-scale data. It has videos covering all sorts of real-world experience humans have. From assembling an IKEA chair to cook a nice meal. It's great, but it's not from robot perspective. And it's passive, it's not interactive. It doesn't give reward. However, we can use internet-scale data to build world model and use world model to generate synthetic training data in robots' perspective and provide reward to train robots. In addition to use world model to generate synthetic data, we can also use physics simulation engine that this community have excelled in building for decades. With this synthetic data, we have a better chance to bring humanoid AI into reality. None of this data is meant to be a replacement of in-robot data. In robot data, you have this observation and action pair. It's important to link the observation space to action space so the robot knows how to act when it puts in an environment. We believe with synthetic data, we can help reduce the burden in creating a huge amount of in-robot data to help accelerate the development of humanoid robot AI. So here we're gonna define what we mean by world model. I'm gonna take a more general definition. I'm gonna define world model as a generative training facility. It's like the Matrix in the Matrix movie. Remember the main character Neo learned Chinese Kung Fu in the dream through Matrix. What we mean by generative training facility is a matrix for robot to acquire skill in the simulated world. This world model takes 3 inputs. The policy, usually you can think it's as a controller to guide, to control the joints of robot to complete the action. Environment, the environment that you want the robot to act on. It can be a kitchen, it can be a dojo. The task can be cook a pizza or learn Chinese Kung Fu. And through this world model, it gives you an updated policy that can do can cook pizza or do Chinese Kung Fu. So it's a policy in to the world model, improve, and then you have an updated policy to achieve the task. This is a grand mission, what we want to achieve with this world model. Before we achieve it, the component we build along the way can be usable by itself. It will give you synthetic data generation. It will also give you policy verification. You claim your policy can cook pizza. How do you verify it's correct, right? Instead of have 1,000 kitchen and test your robot, you can test in the dream. And also, for this generative training facility to understand what happening, the interaction between the humanoid robot and the world, it had to have a great sense about the world. It had to have a great common sense and be able to do the reasoning. So this component built along the way toward this matrix gonna be useful for many applications. Let's take a deeper look. So here we have the world model, policy, environment, and task. When we only input one environment, one task, what you have is an updated policy capable of performing that one skill in that one environment. Now let's start to augment the environment. Instead of one kitchen, let's have 1,000 kitchens, 1,000,000 kitchens. Now the updated policy should be capable in operating in these 1,000,000 kitchens. Because it can operate in so many kitchens, it can operate in unseen kitchen. Similarly for tasks, right? Instead of one task, it can be multiple tasks, cut tomato into slices, retrieve the pizza from the refrigerator, and also different things. When you augment the task space, then you have the robot policy that can accomplish many tasks, have many skills in one environment. And because it can accomplish many skills, many tasks, it's a possibility that it can generate to unseen skill, unseen during training. If we augment in both dimensions, environment and tasks, and we're gonna have powerful humanoid robot like us can accomplish various tasks in various environments. Here, we show the generative training facility inner loop. In this matrix, we believe you need to have two fundamental models, foundation models inside. One is the world generation model, the other is the world understanding model. On the left-hand side, you have the ST, which is the state of the world. The state of the world is perceived by the robot, perceived by the policy. Based on the state of the world, you ask the robot to open the refrigerator door to retrieve the pizza, right? The robot look at the kitchen and then approach the refrigerator, about to open it, right? You take the action. As you open the refrigerator door, you start to see the inside, see the food inside the refrigerator. And this action is consumed by the world generation model to update the state, to start to visualize what's inside the refrigerator, right? So we keep doing this. And in the end, when the robot finished, how do we know the robot really achieved, really did the job? We have this world understanding model, look at the world, and see whether the pizza is retrieved, whether the pizza is put into oven, whether the robot remember to click the button to start the cooking. Right? We have this world understanding model check whether each step is accomplished. And based on the degree of accomplishment, we give reward. The reward is used to update the policy to become a better policy. That's how we envision that generative training facility gonna help us produce better humanoid AI. I'm super excited here to announce NVIDIA Cosmos World Foundation Model platforms. It has both world generation model and world understanding model. Since our release early this year, it had 2 million downloads already. All our source code, including how to train the model from scratch and how to post-train the model, are available in GitHub in Apache 2 license. So it's free for commercial use. All our pre-trained models, the world generation model and world understanding model, are in Hugging Face under NVIDIA Open Model License, free for commercial use. And we have 3 main models in the Cosmos World Foundation model platform. The first is Cosmos Predict. It's a future state generation model. And Cosmos Transfer is a photorealistic world state augmentation model. The last one is Cosmos Reason. It's a physical AI reasoning model. Cosmos Predict is a model, take the current observation, the current frame you observe, and the text prompt, what you want to see next. And camera trajectory, the viewpoints you want to see. These three inputs go to the Cosmos Predict model, and the Cosmos Predict model generates the future states. Here we have a robot, the initial state. Robot's hand is on the apple, and the text prompt is puts the apple in the bowl. And then you see the Cosmos Predict generate the corresponding video. We also have this Cosmos Transfer model. It's a photorealistic world state augmentation model. On the left-hand side, you have various inputs, including segmentation, LiDAR scan, HD map, and bounding bar representing how cars move. These inputs go to the Cosmos Transfer, and what comes out is a photorealistic video matching the description in the input. This model can be used for generative simulation. You take a real video, you extract the world scenario representation, the HD map, and the moving cars as bounding boxes. And through this prompt, then you can create output video with different diverse appearances, like driving in cherry blossom, nighttime, or even with fire. Cosmos Transfer also allows you to generate multi-views. Most of the cars have multiple cameras. To create a valid world model for those cars, you need to have a multi-view generation capabilities, like what we show in the bottom right. And with this world scenario representation, we can perform simple editing. Editing an animal in front of a car. To simulate challenging scenario, we want our self-driving car to be able to handle well. And also like change the lighting condition. Here comes the Cosmos Reason model, our latest model. It's a physical AI reasoning model. Take a video as input, through vision encoder become a set of tokens with the text prompts, enter the LLM backbone. It does the chain of thoughts reasoning trace generation before come out with the final answer. It can be used for annotate a video, provide critique, planning, or can be post-trained as a vision language action model, so the robot can take action to complete the task. So here show two examples. The video in the left, we ask Cosmos Reason model to provide a dense description of the video. What Cosmos Reason did was to first analyze the scene, creating the chain of thought reasoning trace, analyze each component, and finally give a dense description about the video. On the right-hand side, we ask Cosmos Reason whether the worker is wearing a hard hat and have a proper harness. The Cosmos Reason model analyze the video, generate the chain of thought reasoning trace before give the correct answer. We believe this physical AI reasoning capability is super important to help solve the most challenging tasks in physical AI. This bell shape shows the distribution of cases. And usually the most ambiguous, most challenging case are the corner cases on heavy tail distributions. These cases, we can leverage reasoning capability to come out with good answer. And reasoning might take more token to generate, may not be appropriate for real time. But you can do offline computation to generate those great reasoning traits, come out with a great action, and this becomes training data to train a smaller model that is suitable to be deployed in robot for real-time reactions. So I've talked about the Cosmos Predict model, Transfer model, and Reason model. Now let's play a video to show how they are they can be put together to help with physical AI.
Robotics has captured our imagination. Building a truly intelligent robot requires a large amount of training data, but capturing real-world training data, or manually creating enough synthetic data, is expensive and time-consuming. By combining computer graphics with AI, we can help robots learn faster and better understand the real world. NVIDIA Cosmos is a world foundation model platform built for developers to generate the required training data at an industrial scale. Cosmos Predict generates realistic training data from an initial observation, creating diverse action variations using text prompts or action triggers. It also supports multi-view outputs, providing different perspectives from a single frame, especially useful for autonomous vehicles and multi-camera robots. In parallel, Cosmos Transfer takes 3D renders or even real-world video and applies appearance variations, adjusting materials and lighting, weather, and environments to train models that generalize across domains while preserving physical accuracy. Generated videos are then processed by Cosmos Reason, a vision language model that filters low-quality samples, annotates scenes, and supports policy training. Its spatial and temporal reasoning enables safe, efficient decision-making, a great backbone for vision language action models. Cosmos World Foundation models are adaptable. Once trained, they can be post-trained to fit different sensors and perspectives. With the fusion of AI and computer graphics, developers can use Cosmos to help robots and autonomous machines safely step into the real world.
I hope you enjoy our presentations. We believe we are now in graphics 3.0. From rasterization, ray tracing, to be now super powered by generative AI. In this presentation, Aaron talked about how AI can help graphics and how graphics can in return help AI. Sanja talked about how word reconstruction to help train physical AI. And I present the Cosmos World Foundation model platform contain the predict, transfer, and reason models. This year, NVIDIA has 16 papers in SIGGRAPH. Here are a few. I encourage you to attend the sessions, talk to the authors to learn more about their journey with their research work. We also have 3 workshops, a lab session, an RTS rendering day, and OpenUSD Day. I will give a more detailed presentation on Cosmos in the OpenUSD Day. If you are interested, please join my session. Finally, we are hiring. We are looking for people who want to build Cosmos World Foundation model with us to join our mission. We are looking for researchers and engineers. If you're interested, please drop me an email. Thank you so much.